Good morning, everybody, and welcome to this month's webinar by Sigma-HSE on understanding fire and explosion properties of dusts and powders and how we get an understanding of how these materials can explode or burst into flame. I'm Andrew Fowler. I'm currently the Technical and Operations Director of Sigma. I'm having a little bit of difficulty technically here in moving my slides forward. There we go. So what I'll be covering today is a brief introduction to the ATEX legislation in the UK that's enshrined in what's called the DSEA legislation, the Dangerous Substances and Explosive Atmosphere Regulation. So I'll take you through 5 minutes of that, and then we'll look at how we can actually test the flammability and explosibility data specifically for powders, although I will mention a little bit about vapors and gases. And I'll take you through some bespoke testing that we occasionally do, because of course most of the testing that is done for flammability and explosibility is carried out according to well-known and well-established testing techniques. So they're all covered by standards, of which we are accredited testing laboratory for those standards. Okay, so just to give you a brief introduction of who Sigma-HSE are, we're a global company headquartered in Winchester in the UK, but have also got offices in India, and one that we recently opened about 2 years ago in New Brunswick in the USA. And we've also got the luxury of having, along with the consultancy arm, laboratories. So we've got laboratories in Winchester where we do this sort of testing, and we've also got a laboratory based in Hyderabad in India now. So, you know, global presence. What do we do? Essentially, 3 strands to what we do, really. We're a process safety management consultancy, so we can tackle most elements of process safety. It's only the environmental side that we don't currently have the competence to do environmental risk assessments and so on, although we do have links with associate bodies that can do those sorts of things. So anything to do with process safety consultancy, that's dealing with fires, explosions, toxic releases, all of which could cause significant harm to populations, to businesses and so on. As I said, we've also got the testing laboratories, and we're also a well-respected training organisation where we can train companies in a bespoke fashion around their processes regarding process safety or DSEA or testing or whatever else. Okay. So that's just a brief overview of the sorts of things we can get up to. So although I'm talking today about flammability testing of powders, we can indeed do that testing on gases and vapors and mixtures of those and liquids, things like flashpoint and so on. We can also do chemical reaction hazards. So we have calorimeters and various techniques like differential scanning calorimetry and all of that to get a good handle on process control and how to make your chemical reactions safe, which is essentially trying to prevent or deal with chemical decompositions or exothermic chemical reactions, which can cause an awful lot of damage. And there's been many significant incidents that have occurred worldwide over the years. And as I've said just now, we can do testing across all of these, so we can really pull apart the materials and the processes how those materials are used in a really systematic and methodical way. So let's have a brief overview of the legislation. I mean, what the national implementation of ATEX in the UK is DSEA, the Dangerous Substances in Explosive Atmosphere regulations, are trying to do is to prevent or mitigate fires and explosions that occur from using dangerous substances, those classified as flammable, extremely flammable, highly flammable, oxidizing, explosives, and so on. Okay. And essentially what this means is for something to burst into flame, a combustion reaction needs to occur. And all the combustion reaction really is a chemical reaction between a fuel and air. And that's what's termed an explosive or flammable atmosphere. So this is based around the fire triangle, if you like, for something to burst into flame, we need a fuel, we need a oxidant, which is generally air, but doesn't have to be, could be oxygen or other oxidizing materials, and an ignition source. And if we can avoid one of those, then we won't have a fire. So if we can avoid the mixing of the fuel vapor or gas with, or powder indeed, with air, we can avoid the explosive atmosphere. That will prevent us from having an explosion. Or if we can eliminate ignition sources, so we can have the flammable atmosphere, but we're not able to ignite it. That in itself is a quite difficult thing to do. I mean, as a process safety specialist, you're brought up where elimination of ignition sources is very low down on the hierarchy of control of hazards. And the reason for that is it's very difficult to eliminate all potential effective ignition sources all of the time. And that means, of course, that the legislation on managing these sorts of risks also includes dealing with when you do have an ignited event, when we do fulfill the fire triangle and we have an ignited event, then how do we deal with it? Because we don't want to harm anybody. So there's ways around that, which is known as the basis of safety, which includes things around explosion prevention, removal of ignition sources, removal of flammable atmospheres, but also includes explosion protection, things like explosion relief on containment systems, or containment, so the explosion doesn't leave the containment system and doesn't do anybody any harm, or suppression. So that basically means that that ignited event is detected extremely early and is then prevented from progressing by suppressing that explosion, either injecting in extinguishant or keeping it confined within a limited space by fast acting valves and this sort of thing. Okay. Now it's worth saying that the DSEA legislation really only deals with operational weeps and seeps. It's not really considering major accident and hazards, although you will have these controls even for those, but that's a different risk assessment altogether, really. But what it's looking at is where can these flammable atmospheres be generated within our processes. And part of that, the first part of that, is understanding the flammability characteristics of the dangerous substances that we are using. Now, when we consider dust, the things that we need to take care of, first of all, is the actual dust, is the powder that we're handling, is it actually flammable or combustible when it's raised into a dust cloud, or indeed if it's just sitting there as a layer of product. And just like vapors and gases, we need to be within certain explosible limits. So if there's too much powder or too much fuel, then the mixture will be too rich to burn. And if there's too much air within the flammable atmosphere, the explosion, the mixture will be too lean to burn. So we need to be when you'll be aware of this from flammable liquids and things like that. which because it's vapors that burn rather than liquids. Liquids don't burn, it's the vapors given off from them, and we know that as we increase the temperature of a liquid, it will generate more vapors, and it's the vapors that will mix with the air. And we'll, with liquids, we generally talk about the flash point, which is the minimum temperature at which a vapor air mixture will ignite, and that results in the flash point. So if we can operate at temperatures below the flash point, then in a sense we're safe, because there's insufficient energy. Okay, and this is one of the things, although we've got the fire triangle that says we've got to have an ignition source within that fire triangle, as well as the flammable atmosphere within the correct concentrations, there's an amount of, the question is then raised, well, how much energy do we actually need to ignite that thing? Because as I said before, this is just a combustion reaction. It's just a chemical reaction. And when we do chemical reactions, generally the energy of the reactants is higher than the energy of the resulting products. And therefore heat is given out, because combustion is an exothermic reaction. That's why we end up with flame, generation of heat. But reactions generally don't occur until we have some energy input. So there's an activation energy that we need to put into the reactants to get the reaction to kick off. Okay, and of course that can differ dependent on the substances we're involving. We may have to put a large amount of energy into the system, operate at higher temperatures and pressures, for example, or we need very little energy input. And this is where the minimum ignition energy comes in, which I'll talk about a little bit later. Okay, so we need a sufficiently energetic ignition source. We need that blend, that mixture of air and the fuel that's capable of undertaking this combustion reaction. Okay, and when we get to an explosion, the difference between a fire and explosion is that we have, nice little sound effect there, we need confinement or congestion, which gives us flame acceleration. And if we get flame acceleration, we'll start developing forces. It's just Newton's second law of motion, really. If I accelerate a mass of flame, I generate a force, and that's the explosion over pressure. Okay, and to get that to occur, especially with powders, really, to get an explosion, we need good intimate mixing between the powder, or indeed the vapor and gas, and the air. Okay, although obviously it's easier to achieve with vapors and air to get that good mixing. So the first test that we need to do is find out whether or not a powder, or the dust from a powder, is explosible or not. Will it undergo this this combustion reaction? And basically the combustion reaction is simply an oxidation. So anything that isn't fully oxidized is capable of being combusted, of undergoing that oxidation reaction. So something, for example, like carbon dioxide or sodium sulfate, sodium chloride, they're fully oxidized materials already, so they won't be able to partake in this reaction. But anything else, alcohols, ketones, polymers, any hydroxyl groups and so on present there, could be oxidized. Okay, so many common powders, many of the products that you will produce, organic powders, will in fact be capable of combustion. So if the powder is dispersed in air and we have an ignition source, then that reaction could well occur. So a simple test there for doing that, I'll take you through in a couple of minutes. It's known as the A/B test. So we do the test. If we get a ball of flame coming out of the test apparatus, then the powder is flammable. We call it a group A powder. And if it's not, we'll call it a group B. If it's non-flammable, if we don't get that ball of flame, it's a group B powder. Okay. Now, all of the tests that I'm going to talk about typically are all based on the standards, as I said before, and they're all tests done under ambient conditions. Okay. Because that's the way the standards have been written, and that's the way that most of your processes will operate with these powders. You know, even if you're on a food manufacturing site handling powders which are combustible, because many of those common food ingredients, sugar, flour, starches, they are all capable of oxidation. They are all combustible powders. Okay, so let's have a look at how we're going to carry out some of these testing. And I'm going to take you through some of these. I'll take you through how we determine minimum ignition energies and temperatures, how we determine explosivity characteristics like the pressure that's involved and the rate of pressure rise, and things around the minimum explosive concentration and limited oxygen concentration. So, you know, the group B powder is done in equipment just like this, really. We've got a glass tube there. We've got a couple of electrodes which we can pass a spark through, and we put a very small sample, a few milligrams of sample, in the base of the equipment, and by using a blast of air we can generate a flammable cloud, a dust mixture in air, and a few milliseconds later we can pass a spark discharge across those two igniters there, and we can see if the material ignites or not, whether we burst into flame or it doesn't. And it's as simple as that, and that's the group A/B test. And when we do the group A/B test, all done at atmospheric conditions, as I say, but the energy that we put into that spark discharge is a few kilojoules. It's a very large amount of energy. And it's fair to say that in most processing operations, if we forget about lightning strikes, most energy sources will not generate kilojoules of energy. But it's just the case of, is it combustible or not? Now, to be able to use this sort of data, once we know that our powder is capable of combustion, then of course we need to get a bit cleverer, because we're going to make our processes safe enough to handle this. So we need to get a handle on what's the minimum amount of ignition energy that we can put into that system. So instead of putting a few kilojoules through these electrodes, we use very similar apparatus, but we're able to alter the amount of energy that we can put into that spark discharge. So we can determine, you know, we can keep reducing the energy until the dust air mixture doesn't ignite. And the other way that we can do this, we can also generate that spark discharge in two ways. We can generate that spark discharge by discharging a couple of capacitors, capacitive discharge, and that gives us a handle, without going into the physics in this webinar, that gives us a handle on the spark discharges that may be generated during an electrostatic discharge. Now, obviously, we can put energy into dust clouds from mechanical sparking and also temperature. So to mimic mechanical sparking, the energies involved there, what the test requires us to do is to generate that spark discharge inductively. So it's just a different way of doing it, but you'll find that when you ask us to determine the minimum ignition energy, we will, for powders, we will in fact carry this test out both capacitively and inductively, and give our opinion on how likely that dust air mixture will ignite under different conditions from different types of ignition source. Yeah. And then, of course, once we have the output from that, we can ensure that, you know, if the energy that we can create in our processes, either electrostatically or mechanically, if that is actually less than the minimum ignition energy of the material that we've determined, then those won't be effective ignition sources for that dust cloud. So just some examples here of different materials of what the minimum ignition energies are of certain materials. You can see foodstuff there of starch, where we require 100 to 300 millijoules. Remember before when we were doing the group A/B test, I was talking about kilojoules of energy we were putting into that dust cloud. Sugar and other foodstuff only requires 10 to 30 millijoules. And when we start talking about metal dusts, we can go low, we can get even lower. And some active pharmaceutical ingredients, in fact, quite a lot of active pharmaceutical ingredients, require very little minimum ignition energy to get them to kick off. Now, if we can, you know, if I give you a comparison here, you know, in terms of generating electrostatic discharge energy, just walking around the place as a human, we generate electrostatic charge. And a human is capable, if a spark discharge occurs, and we've all come across this, you know, when we're walking around and we grab the door handle and we get a little spark, that's a spark discharge. That spark discharge from us is around the 10 to 30 millijoules. Okay, so there's enough energy there if we are not effectively earthed as people to ignite aluminium, dust, and many APIs. So we can use this knowledge of the minimum ignition energy to make sure that the precautions that we take in our process can't generate that amount of energy. Okay. The other way of putting energy into the system that we all know and love is temperature. So this equipment is used to determine the minimum ignition temperature. And this, we're measuring the minimum ignition temperature here of a dust cloud. Not just a layer of dust, but the dust cloud. So it's equivalent, if you like, to the auto-ignition temperature for vapors and liquids. Okay? And you can see it's quite simple. We just heat we have an insulated system, we heat the system up, and we're looking for disperse that dust cloud in there at a certain temperature. When we do minimum ignition temperatures of dust clouds for powders, we generally do the layer ignition temperature as well, because when we're handling dust, as you're well aware, we can end up with, if our extraction systems aren't effective enough, or if we spill or not particularly good at housekeeping, of allowing dust layers to build up around our processing operations. And if those dust layers can lie upon equipment that is hot, you know, collecting on a steam pipe or collecting on a hot electric motor, if there may be sufficient energy in there to ignite, to get that layer of powder to burst into flame. And this test here is essentially doing that, where we take a 5mm layer of the material of the powder and we warm it up, and we're looking for the temperature at which it starts to ignite. Okay, and then when we've got these two temperatures, the layer ignition temperature and the minimum ignition temperature for the dust cloud, we apply some safety factors. We take 2/3 of the minimum ignition temperature and we subtract 75 degrees off the layer ignition temperature, and the lower of those two values is what we term the maximum allowable temperature. Okay, so there's a safety factor built in there. And then when if you've got electrical equipment and so on that is, or mechanical equipment that's running at high temperatures within where that flammable atmosphere or layers of powder could be, then we can purchase equipment that can't generate temperatures in excess of this maximum allowable temperature. Okay, so then if we can do that, then we can eliminate igniting dust clouds or igniting layers of dust through temperature, through hot surfaces. Okay, so these are very basic tests, and as I say, they're all done under atmospheric conditions and so on. We've also, we know that all these tests are done to give us that information so we can design our processes to try and prevent ignition. But of course, if we do get ignition and we've got that confinement of mixing of powder with air, we can end up generating that explosion, which is generating pressure. So the 20-litre sphere test is the approved technique, if you like, for determining these things. And as you can see, it's very similar to before, except we do the combustion reaction within a pressure system. So that little spherical thing there is a high integrity, high pressure system. And just like before, we'll put a few milligrams of material in there. We'll generate a dust cloud. We'll put ignition source through the center of that dust cloud. But what we're doing, the results of that is we can measure the maximum explosion pressure. So if you wanted to contain that explosion within your process equipment and not have any explosive effects outside of the containment system, obviously knowledge of the maximum pressure is important. So if that dust vapor explosion can generate 8 bars of pressure, then if our containment system can withstand 10 bars of pressure, we're not going to get any breakout of explosion pressure hazard. Okay, it also measures the rate of pressure rise, the dP by dt. So if you like, how quickly that pressure can be generated. Okay, and this results in what's known as the KST, and we can take the KST value and change that into what's known as ST values. So we group a range of dP by dt values and put them within a certain range that gives us whether it's considered that explosion is a relatively weak explosion or whether it's a relatively strong explosion. Okay, now this information is critical when we're designing our explosion protection systems. And if we're going to use venting, then that vent needs to be sized appropriately, open at a sufficiently low pressure. The fireball needs to be diverted to somewhere that's safe, and so on and so forth. And it's this sort of data, the maximum pressure and your KST values, the rate of pressure rise, that's allows you to be able to design those sorts of systems, whether it's suppression, venting or containment, so it will be effective. So we can do things, if we can do things to try and prevent the generation of a flammable atmosphere, which is either using inertion, for example, so we're removing the oxygen concentration, or having good effective mechanical ventilation, so we can remove any flammable mixtures very quickly at source. Or we can design vents, suppressions or containment to give us explosion protection, so we're not harmed if we do have an ignited event. And this powder, this next slide just gives us these ST values. So we take the KST value, we measure that in the test apparatus. If it's between 0 and less than 200 bar meters per second, we tabulate that as an ST1 dust, and many of our foodstuffs fall into that sort of category. ST2 dusts, KSTs between 200 and 300, cellulose, wood, flour, and ST3 metal dusts and some of our other easily oxidizable, very rapid reaction materials that can be oxidized rapidly would be KST 300s. Okay, and what it basically means is if you use venting as a means of protection, you'd need a larger vent area that opens at a lower pressure for an ST3 type explosion than you would for an ST1 type explosion. Now, just like with vapors and gases, where we need to be within these explosible limits, the same thing is true for dusts. Yeah, so the minimum explosible concentration, which is measured in the 20-litre sphere test, we can generate dust clouds of different concentrations effectively, and we can see what's the lowest explosible concentration by just reducing down. Because really, dust clouds, they need to be quite opaque to really result in an explosion, as this little pictogram is sort of illustrates. So if I had 40 grams per cubic meter of coal dust, and I was trying to look at a 25-watt bulb through 2 meters of this dust cloud, I wouldn't actually be able to see that 25-watt bulb through 2 meters of a 40 gram per cubic meter coal dust. So that's quite a dust concentration, really. And sometimes these things can't be calculated. All the things I've been talking about when you come to powders are not calculable. And the reason why they're really not calculable is because with dust, the reaction dynamics, the reaction kinetics are due to particle size distribution. And the finer the dust, we know, for example, that powders with particle size greater than 500 microns really don't partake in dust explosions. We need to be less than 500 microns dust diameter. And that means that we're looking at, when we do these testings, even though we may have a material that's only got a fraction of fine material in it that's less than 500 micron, the standards dictate that we do in fact sieve, and we do the test, the AB test and the MIE tests and so on and so forth on the finest material. And the reason why this is the case is that's where we're likely to get our ignitions from and our explosions from, sorry. But there will be elements within your process where, for example, you are deliberately collecting the finest material. So your dust extraction systems, for example, will, if they're effective, be taking out the finest material. Okay, or within the head spaces of your mixes, in your mixers or hoppers or things like that, when we're dropping the powder through free space. So, you can imagine, again, it's done in the 20-litre sphere test, and we just alter the amount of concentration. The other way we can prevent ignition is ensuring that we don't have sufficient oxygen for that material to undertake the combustion reaction. Okay, so again, we can measure this by reducing the amount of oxygen present in our air. And again, this is something that is not easily calculable, especially for powders. So you've got to get that test. So if you're using inertion as part of your basis of safety, for example, you're inerting with nitrogen, then you can see from the table that dependent on the substance, the powder you're using, that limiting oxygen concentration can vary quite dramatically. Remember that general air is 21%, so something like a rye flour, we only need to get down to 13% air to prevent ignition, where something like aluminium or sulfur, we need to get a lot lower down. Okay, and the reason why we can't we have to measure these things, and they're not easy to calculate, is because particle size is so important. It's not really an issue with gases and vapors. You know, you can go to the standard text, chemical engineering textbooks, and they'll tell you what the auto-ignition temperatures and the limited oxygen concentrations are for liquids and vapors. That doesn't really exist for powders, although you will see it quoted, but what you very rarely see quoted is what the actual particle size distribution is of the material that they're quoting that value from. So if you've got a dustier material, you know, it'll go earlier, it'll have lower ignition energy, and so on and so forth. Again, picture it like a solid gas reaction, this oxidation reaction. As we decrease particle size, we increase the surface area. There's more sites for those reactions to occur. We can't get any heat generated from those reactions won't be conducted away easily if it's not in the bulk. Okay, and of course we've also got the really difficult things to that we can't calculate, things like the effect of particle shape and surface structure and so on and so forth. Okay, so it really means that we need to do this testing. So those are the sorts of standard tests that we do that give you information that allow you to carry out safe process design and operation of your processes. Okay, have the measures in place to either work below the MIEs or the MITs or whatever. Okay, but and as I've repeatedly said, all the tests are done at atmospheric conditions. So I just want to take you through some of the occasional bespoke testing that we're able to do and have done for clients. So I've got 3 examples, and one basically was we were discussing with one of our clients that operate a coal-fueled smelting furnace, and their primary basis of safety was inertion, nitrogen blanketing. And the question was asked was, does the temperature affect the limited oxygen concentration of a material? Okay. Now, obviously, the process isn't, you know, burning coal fuel. We're not operating at ambient temperatures here. Yeah. So to be able to do this, we had to modify the 20-litre sphere test. Yeah. So as I say, the standard limited oxygen concentration apparatus, we redesigned that and adapted it to provide an elevated temperature test condition. Yeah, so normally on the 20-litre sphere we have a cooling jacket, so we needed to change that to a heating jacket rather than, because we didn't want to cool the reaction vessel, we wanted to heat the system. So that was pretty straightforward, really. So we drained the system's cooling fluid, we replaced it with a glycol mixture, we linked it to a recirculating digital heater fluid bath. Yeah, that was one thing, but we also needed to heat the injection air. So we needed to preheat that. So we were able to make that get a system to connect to our heating system of the main explosion chamber. Okay, that of course means then that we needed to replace the temperature pressure sensors so they were capable of operating at higher ambient temperatures and so on, so that they measured the correct explosion pressure values which weren't affected by the hot system. Okay, we carried out the tests, we modified the equipment, we carried out the tests to answer the client's original question. As it turned out, the limited oxygen concentration for the material was identical to that as it would be at ambient temperatures. So you got a lot of effort for not a particularly interesting answer. But that confirmed to the client that their current oxygen detection system and alarms around their inerting system actually, under their specific operating conditions, would still protect their staff and their process. So I think they were very appreciative of that. Another example was, for most processes, air makes up the atmosphere in which the material is either created or processed in. However, in some cases, the actual process conditions are a hybrid scenario formed of other gases and vapours, along with the product being processed or formed. And this was the case for this particular client that we worked with, who produced carbon and acetylene black powders. And the atmosphere that's present there when they're doing that process is a mixture of acetylene gas, oxygen gas, nitrogen gas, carbon monoxide, hydrogen, and carbon dioxide. Okay? And they originally came to us and said, can we establish the material's limited oxygen concentration in this gas mixture? And we gave this a fair bit of thought, and we advised that even though there are high levels of flammable gases present within the system, the oxygen concentration that's present is already low enough to render the mixture non-flammable, because it's below the limited oxygen concentration of both flammable components, of both the acetylene and the hydrogen. Okay. But what we did consider was we devised a program for testing of the acetylene black for dust combustibility within these specific gas mixtures. Yeah. And acetylene black is a weakly combustible material, a ST1 if you like. So the theory is that this weakly combustible acetylene black will not be combustible in the atmosphere it's processed in, and therefore can be used as a basis of safety. Okay, so that was another bespoke piece of testing that said, yep, no, you're safe. The way you're manufacturing this equipment, it's the way you're manufacturing this product is not really an issue to you from a fire explosion point of view. But of course, in this same production process, it wasn't the only issue. Yeah, because this material at startup in the process is processed in air, and therefore we know, because the acetylene black is an ST1 dust, we know it's capable of combustion, and we've got a flammable atmosphere here where we've got the powder dispersed in air. We know it's weakly combustible, but the problem is acetylene black is extremely conductive. And therefore, if we want to determine the minimum ignition energy, it's not really easy in the standard equipment. The problem is the material, because it's highly conductive, coats the explosion vessel, and it creates a short circuit between the high voltage and earth electrodes that we use to produce the spark of known energy. So under those conditions, we wouldn't be able to determine the minimum ignition energy for this powder in the normal way. So again, we adapted our dust combustibility 20 litre sphere test. Why we did this was because that was capable of handling conductive powders, but rather than using the standard sort of chemical ignition sources that produce the ignition of the dust, we managed to purchase chemical igniters of differing energy outputs. So this allowed us then to get an effective minimum ignition energy. It's just outside of the normal MIE accredited test procedure. Okay, so we ended up measuring the MIE by using the 20-litre sphere test with a selection of different ignition energy igniters. So hopefully you can see that, you know, we understand what we do in a very concise way. Hopefully you've got some examples there of how we can help you, even if the standard test equipment isn't the most appropriate test or would not give us the correct answers to allow you to ensure that your processes are safe. And those are just 3 examples there of how we've helped clients in the past and continue to help clients with more bespoke testing and consultancy. So essentially that's all I've got to say for today. As in every webinar, you know, if you've got questions, please send them through. You can either call us up or send us an email to info@sigma-hse.com, and we'll help in any way that we can. So I hope the past 45 minutes has been useful to you, and I'll say my goodbyes and thank you very much, and hopefully see you next month for our next exciting webinar. So cheerio and bye bye. Have a good day.